Hey, John here. Let's talk about sound. And Wikipedia has a couple of nice pages in here that we can look through to learn a few things, and then apply that by running a program that generates sound files we can play back and recognize what's going on. Remember what sound is, right? Sound is a vibration that propagates through an acoustic wave and blah, 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 right? Look, scroll down here. The bottom line is this. Sound is a pressure in the air that we breathe. This graph here kind of represents a notion of a high pressure followed by a low pressure that's traveling through space, okay? Now, depending on how those pressures relate to each other over the course of time, you can draw a plot that shows the high and low pressures, okay? That's what you see down here in this diagram right here. So let's have a look-see at what this is all about. So what is this graph here showing us? It's showing us the relative pressure over the course of time. And notice this thing repeats itself. So we have a low pressure, followed high, low, and then a little bit of a wiggle down here, followed by low pressure, and then it repeats itself. It repeats itself again and again and again. All right? Now we're going to see what happens here is the shape of each of these things that repeats, this wave here, this cycle that repeats. What this cycle represents and the shape of these changing pressure over time will create a distinctive sound to our ears that we could recognize as something. For example, this is the sound of an oboe. If you plot pressure over time of the sound coming out of that instrument. Now, let's look into the details of what that really means, all right? We don't have to worry about history and things like that. It boils down to the fact that if we're going to talk about sound, we want to record sound, we want to play back sound, we need to kind of understand what it is, right? So it is varying pressure over time. Now, we can look at sound and describe it using 6 different traits, okay? Bird's eye view here. We got pitch, duration, loudness, timbre, sonic texture, and spatial location. Now, let's look at these one at a time. Pitch. We just looked at this diagram a second ago. Let's have another look at it with a different label on it. The pitch is basically the frequency. It's the rate at which these cycles of pressure changes repeat themselves. Higher the pitch, the higher the frequency. The duration, well, that's simple. It literally is the duration. This thing refers to how long the sound is on before it turns off, right? So down here, this graph here with this straight line over here represents no change in pressure over time. You perceive that as silence, okay? So you have sound for this long of a period of time, for however long the time is that's represented by the X scale in this particular graph. Now, loudness is how we describe the amplitude of these waves for the most part, okay? There's 2 different things that kind of come into play here, but the simplest is the overall amplitude. Notice the size of the waveform here. It has a high amplitude for the distance from the bottom to the top, all right? And this represents the perceived loudness of the sound. Bigger oval, louder sound. This is the same exact waveform down here, except it is a smaller amplitude, okay? So you can see it as, the 2 big peaks followed by the little foothill over there. And because it is a smaller amplitude, you're going to hear it as a quieter sound. This middle one here, you'll notice that this the waveform, the shape of this wave is a little different than the one up here. The shape of this wave is what we call a sine wave, because this is the sine function here, okay? And because the sine wave is a little more pure than this one up here, this one's got a lot going on inside here. Your brain, even though these two have the same amplitude, your brain might consider this one to seem louder, and that's what this is showing in here. If I have a sine wave, even if it's the same amplitude as this oboe up here, the sine wave is a pure and clean sound, and it may not be perceived as being as loud as an oboe whose sound has the same amplitude. All right, so timbre as Wikipedia discusses over here, has to do with what the sound does beyond a simple single cycle of the wave, right? So let's say we're playing this wind instrument here, and we look at a very small section of time while a note is being played. We see this familiar waveform we've seen before, okay? Now, if we take a step back and look at it over the full time that someone was blowing into it to the time they stop, look what else is going on. We have what we call an attack, which is the rate at which the sound amplitude ramps up in the beginning of a sound. It then has a decay, which is this little reduction here, which could be 0 depending on the instrument. It then has a sustain, and then it has this release over here. So you see the sustain is here, and then it kind of tapers down a little bit, and then it goes down very quickly, almost geometric here, okay? So that is the timbre of the sound. If you come down here and look at what happens when you hammer a key on a piano, again, we can look at the little teeny wave here in any one little small segment of this wave here. But if we take a step back, we'll notice this thing, the attack is much more swift on a piano, and that makes sense if you ever look inside it. It literally has a hammer that smacks down on a string. It then has a little bit of a decay. The sustain sits there for a while like this, and then the release is this geometric reduction in amplitude over this amount of time here. So it's this relationship of getting loud and quiet over time, combined with the shape of the individual waveform of each of the cycles that are coming out of this instrument, that your brain recognizes as a piano versus an oboe or a clarinet or whatever this thing is. I don't actually play wind instruments, so I don't know. Sorry. Leave a message in the notes below. Anyway, as you can see, once again, you've got this wind instrument with a double peak and this foothill with a big spike there. And the piano has a double peak, but not as big a valley. Right? And it also has a foothill, but this initial spike on the foothill for a piano is not as big as the one is, relatively speaking, as it is for this wind instrument up here, okay? You would also see that this double peak, this beginning of the double peak, this has a bit of an angled swoop before it rises up here. And your mind definitely can tell the difference between these two waveforms here. Okay, so that all combined, this fact that the waveform, each of the individual cycles here is different between these two instruments, and what happens during the attack, decay, sustain, and release is different of these two instruments as well. And when they talk about sonic texture here, what they're referring to now is what happens when you play multiple things at the same time, more than one sound taking place simultaneously. In particular, what we're talking about is like an orchestration of multiple sounds, okay? Now, it can also refer to something like a cacophony, like in a busy cafe full of a bunch of people talking at the same time, making a lot of noise. And last but not least, we have this spatial location. Now, this refers to things like what the sound, how the sound interacts with its surroundings, right? If you're in a room like a concrete walled room, there's a lot of echo going on in there. And at some frequencies, it might even resonate, okay? So that has to do with the spatial location. And as they point out, your brain can actually extract one sound out of a whole bunch of sounds by taking into consideration this spatial location, the timbre, and things like that, right? And that's why you can actually pick out the sound of like an oboe in a whole orchestra. You can hear an instrument playing in there, and you can recognize that that's an oboe or something like that, right? Or if you're in a noisy cocktail party and you're listening to a single person speaking, you can actually recognize and understand their words. Now, let's take a look at these first four: pitch, duration, loudness, and timbre. I'm not that concerned about these two down here right now, because where we're going is we want to understand how to make sound from a computer, and we're not going to, and we only have so much time. So let's stick to the basics here. Now, as the graphs of changing pressure over time showed us, we can record and play back sound by just simply taking note of what all the different pressures are over the course of time. And that's all we really do when we record and play back sound. All right. Now, the method that we're going to talk about is called pulse code modulation, or more specifically, linear pulse code modulation. So, as they say, this is a method that we use to digitally represent analog signals. Okay, this is the heart of digital audio. Okay, it's how compact discs work, digital telephony, and all the sound files ultimately on your PCs and phones. Okay, now linear pulse code modulation is a subset of the more general pulse code modulation, in that what we're speaking about here is when we quantize these pressure levels, we're going to use a linear scale. And as they point out, you could do it if you wanted to using some other function. You could use a logarithmic function. And there are some alternate standard methods out there called A law and mu law. I'm not going to get into the details other than to point out that the reason that they're different is because if you study the psychology of hearing, your ears are more sensitive to small differences in sound when the amplitude of the sound is small. And if you have a loud sound, a high amplitude, and you have a very small and subtle difference in the volume or the pressures there, you're not as apt to recognize that, okay? Now, these algorithms down here, these are nonlinear, and they take that into account to try to improve the overall quality of the reproduced sound. Now, the reason they do that is so that they can record it using less bits of data. Okay, we're going to just waste the bits in this example. We're going to build a CD quality audio file from scratch using 16-bit audio. That's what this thing up here refers to. Usually when you're going to get into A law and mu law, you're trying to compress the number of bits that you're using down to 8 bits or something like that, okay? I'm not going to talk about compression here, all right? I'm just be it known, recognize these names, and they're referring to a little bit better quality audio when you're using a more compressed waveform. So we talk about how a stream has two basic properties that determine the fidelity, the quality, right, of how well the recording can reproduce the original analog signal, right? And that is the sampling rate, which is how often we sample the pressure, and how many bits we use to represent the total number of possible different pressures that we can recognize. All right. Now we can look at that in a graph down here. Let's scroll. We can read about the history and why it is and so on. This is what we came for right here. Okay. So how do we create sound? How do we reproduce sound? How do we record it? Okay. Look at this graph here. These vertical gray lines represent the sample rate. If time is on this axis here, the x-axis being time, the question is how often do we check the pressure, right? If this red line represents this is a sine wave, and the pressure increases, then decreases, then increases. So this is one cycle, or what we call one period of this wave. Okay, so how many samples, right? 1, 2, how many, these blue dots? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times 2, presumably. So this has 26 samples over the entire period of this wave. So depending on what the x-axis is, if this was 1 second, we would be sampling at 26 samples per second, or we would say 26 hertz. So that's what they mean when they talk about the sample rate. Now, these horizontal gray lines represent, these are all the total number of possible values that in this particular scenario that can be represented when the pressure of the signal has been measured. All right? So we're going to do 26 samples per second And what we're going to do is we're going to represent any one of what you can see are 16 different levels of pressure. And this is a linear scale because the distance between all these horizontal lines are equal, right? So this is linear pulse code modulation. And in this example, I'm stating that this is 1 second. So the sample rate is 26 samples per second. And the number of bits per sample here, well, obviously, you can represent 16 values in 4 bits of binary data. So this looks like a 4-bit linear PCM waveform. And in order to reproduce it, what happens is you measure the pressure at time 0 over here, and the closest value is this 8 right here. So you have to round it off. You say that's the pressure at this time right here. 1/26th of a second later, you measure it again. And you see, again, the red line, the closest value of the 16 possible values that you're using to represent the current pressure at this time is right here. 26th of a second later, you sample it again. This one's right on. So you got lucky that time. So there's the pressure there. 26th of a second later, you measure it again. Well, what's the closest value that you can express to represent the pressure at this time? Well, you have to round it up a little bit here. And so on. This one's pretty close. And then over here, the closest one is up here. So it actually, when we reproduce this, the wave is not really quite right. It has a flat top, and then it kind of goes over here, and then it jumps down. And then that continues on over here. Now, this is the fact of life if you're going to do a digital sampling of this waveform, all right? Now, obviously, if you have more bits, instead of representing it only one of 16 possible values, you double that, right? Add one more bit. Use a 5-bit value. Well, then what would happen? There would be more of these horizontal lines. There'd be more possible values for all these blue dots go, and you can converge increasingly closer on where the red line really is and get a better quality, okay? A better, as they say, fidelity, right? Another thing you can do is sample it more often. Now, if you look at what we call CD quality recording, digital audio compact disc, okay, what happens is if you flip through here, it tells you where is it? Standard audio format right there. On a CD for digital audio, it uses signed 16-bit linear pulse code modulation sampled at 44,100 hertz, okay? That's why we're here. We are going to create a file using this exact encoding that we can then play back and listen to on our computer. So how do we do that then? We just open up a file and write a bunch of 16-bit values in it? Well, oddly enough, yes, you can do it that way. But if you do a little more work, what happens is you can put what we call a header at the beginning of all these 16-bit samples, and then it will be expressed in a standard format that you can use any old audio player to just play on your PC. Here's one. This file format was invented in the late 80s by Sun Microsystems, and it's still basically the essence of what is in use today. And you see stuff hiding in here. 8-bit mu law, and then you'll see somebody using 8-bit A law. And this PC does it this way, that one does it that way, and so on, all right? Now, here's the beauty. This is all we have to do. You have to create a file. Notice this has got to be in big endian format, okay, including the sample data. Big news flash there, big endian, okay? Why? Sun invented it, and Sun had 68Ks and Sparks in their workstations. Those were big endian machines. So why would they want to waste CPU unraveling little endian data when their native format of all their machines that they sold were big endian anyway? So it comes as no surprise to me that they would have come up with a standard based on big endian format, okay? So what do? How do we make this? Well, this is what we call an SND file. Now, this is old school, really simple, which is what we like, right? We don't have 19 lectures on compression and theory. We want to get to it and make some sound here, okay? So what do? Notice this is a 32-bit unsigned word. The first word is this thing called a magic number. You simply store that in the file. What's the second one? Data offset. This is basically set to the number 24. Just set it to 24. What it represents is how much junk is in this header. Okay? And the next thing is the data size. Now we're supposed to set the total number of size in the file in this field here so that a streaming player knows how long the audio file is. You know, if you play this over the internet or something, and it takes you, 10 minutes to download it, and it's an audio file that would play for 1 hour, your computer really doesn't know how big it is until it's finished downloading. So if you want to, you can put the data size in here, the number of bytes of the whole file, so that your PC can show you that scroll bar. If you don't want to do it, just stick all ones in there. Would you effectively tell your computer it's infinite in size? You figure it out, okay? That's what I'm going to use. It's easier, okay? We'll worry about streaming downloads some other time. Now we've got encoding format. Many options to choose from. Right here, 16-bit linear PCM. That's your CD quality audio. We can have more bits. We can have higher fidelity. We can go up to 32-bit. We can even use a 64-bit floating point value in here. And then down here, notice we'll have mu law and A law and all these other kinds of formats, including what we call adaptive pulse code modulation. I'll let you click on these and find out what all the other ones are later. They all have to do with different kinds of compression, okay? Everybody wants their own way. We're going to use the CD style way here, all right? So we're going to look at data encoding format number 3. That's what we're going to put in this part of the header right there. So what comes after that? We need to let the computer know what the sample rate is. So when it plays back our file, it knows how often to update. Each time we give it one of these values, how often should your PC play the pulse code sample out to the speaker, okay? Now we're going to create a mono file, which means we're going to have one channel. So armed with this, we can create a file. Certainly we can create a file that has silence in it without a problem, right? So let's look at some code that'll write that exact header out the way we need it. Okay, so I wrote a function called write header. And what I'm going to do is I'm going to send out the magic number. I'm going to send out that I have a 24-byte header, which is the number of bytes in these, 6 times 4 byte variables here. Okay, then I'm going to have the data size set to some giant thing, which is, I don't know, you figure it out. We're going to use the encoding number 3, which is 16-bit linear PCM. We're going to use a rate, which is set to some variable that I said above, which is equal to 44,100. And we're going to have one channel. Now, what's this H2BE 32 all about? Well, remember, if you're running this on a PC, and your native data representation for these variables is little endian, then they'll all be backwards when you write them into the file. Now, I'm going to simply write these to standard out. And if I ran this, it would print it all over the screen. And this is binary junk. We'd see just garbage all over the screen if we did this. But I can easily redirect the output into a file, or I can put it into a pipe and pipe it into some other application and stuff like that. All right? This is just real easy to do things like this. This is called a filter application when you're dealing with just writing stuff to standard out. So that you can pipe things together on the command line for ease of use. So I digress. H to B E32, what does this do? This is host to big endian 32-bit value. So what happens is it takes this value here, it interprets it as if it is a 32-bit value in the native host order, which may or may not be big endian. And on a PC, it is little endian, as are most ARM processors. A lot of processors are little endian. Okay, some of them though are big endian. Like I said, a 68K, a Spark in the mainframe and stuff like that. Right. The bottom line is you may not know. So by using this library function, we're guaranteed that whatever this value is over here, it'll be converted to a big endian 32-bit value so that when it is stored in this variable over here, The order and the bytes in memory are appropriate to be written out if you pass it a pointer like this. So what I'm going to do is I'm going to simply write out, I give it a pointer to where this variable is stored in memory, like this one right here. And I'm going to use the size of that variable, which would be 4. All these are just 4. I could have just hard-coded 4 in every one of these if I really wanted to, right? And I'm going to cast this as a character pointer because the way this thing is defined and so on. You can read about the right method of the output file stream on your own time if you want to know more details. The bottom line is this creates the big endian values stored in these variables, and then I can write them out like this into the header of a file. So I can write a program now that, among other things, can write out a header into my file, right? Now we'll look at this in a minute, and we'll look at that in a minute as well. So let's run this and see if the header comes out right. All right, so let's compile it up and run it. Sound pipe hex dump. And see, remember, this is going to generate binary output data, okay? Don't just run this to your screen. It'll print junk. So what does it do? Here's the first byte. That's the so-called magic number. And as the documentation says, if you look at it in ASCII, it'll say .snd, and it does. This field here, what's that one? That one represents this data offset value here, which is supposed to be 24 in decimal, right? Which is 18 in hex. Here's all the FFFF value that says I don't know how long this is. Otherwise, this would be the number of bytes in the file. Okay, this is a big endian 3. That is our encoding value right here. That's 16-bit linear PCM. That looks good. Then what do we got down here? This AC44. Well, that would be the hexadecimal value for 44,100. Okay, and the one right here represents the number of channels. So our header looks good. In fact, if we take this and store it into a file, let's just save it into XXX, right? And I run the file command, and I hit enter. What happens is the file command is really smart. It looks around, it opens up the files and sees what's inside of it, kind of sniffs around a little bit and tries to figure out what it is. And then it tells you about it. This is great news. It figured out that this is a sound file, most likely because it starts with .snd, and it recognizes that. And it says that's the kind of file that Sun and Next computers use. Well, modern day Nexts are Apples, right? It is audio data, 16-bit linear PCM. It's mono, and it has 44,100 hertz as its sample rate. Well, this is awesome news because that's what we wanted to say, right? So now what? Okay, well, let's go back and look at our code. Now, this is some initialization code that's not used right now. We then call this function here called silence, and we give it 1/2. And as the comment over here says, that says generate 1/2 second of silence. Now, we'll look at the code in a minute, but the short of it is this thing generates enough samples in the file to represent 1/2 second of no changes in pressure. Now, think about that. If your sample rate is 44,100 hertz, how do you represent 1/2 second of silence? Well, you write out 22,050 samples whose values are all 0, or at least all the exact same value, so that it describes a waveform that does not change over the course of time. So right now, this program is simply creating the header and filling it up with enough samples to represent 1/2 second of no sound at all. So let's go ahead and open it up with an audio tool and see what's in there, see what it says about it. Now, this is a program called Audacity. It should be available on Macs and Linux and Windows and stuff like that. And we get a little viewer like this. And notice that it's straight lined in here. What we got here, we got a little time scale up there, right? It says 1/2. So this is in seconds. And we've got nothing but all zeros. If we play the file, you'll see a little cursor go through here. It goes pretty quick because it's only 1/2 second of audio right here. And it's perfectly quiet. All right? So far, so good. So let's say we want to fill it up with something that we can recognize as a tone. All right? The simplest waveform that I know to create is a square wave. All right. So this is a bunch of code that's going to generate a square wave, and by that, which, as we'll see, will end up looking like this, where the waveform starts out, it goes up, and it stays high, and it's flat, and then it goes down, and it stays flat, up and flat, and it's this squared off shape is why it's called a square wave. Okay, so that should be easy enough to create some logic to create such a thing, right? So here's my function. We're going to take a duration, a frequency, and an amplitude for this wave here, all right? And the amplitude here is really a scaling factor. So let's look closely at what this code does. Now keep in mind that time is represented by a total number of samples that fills up that file. Remember, for a half a second of silence, it had to write 22,050 samples into it in order to represent all the samples that cover a half a second of time. So if I want to play something for a half a second or a quarter of a second or a whole second, it would be requiring the number of samples, which is the rate, which I define up at the top of the file up here, times the duration. So if it's 1 second times 44,100, I would get 44,100 samples. That makes sense. Okay? Now, the frequency is how often the wave goes up and down and up and down. How long, how many times per second does the cycle repeat itself? Well, the period here represents the amount of time it takes for one cycle to play out. And that's just the inverse of the frequency, okay? And this is going to be in seconds. So, just like the number of samples for this entire duration, how many samples do I need to represent one single cycle of a waveform that's going to make a sound at this frequency right here? Well, that would be then the sample rate again times the period of one single cycle. And if you grab this off my website, you can turn on the debugging and see that all that works if you want to. So with these all calculated, we enter a loop in here. So what do we know? A 16-bit value, the maximum value that we can store in there in hex would be all the bits on with the sign bit of 0. That's 7FFF, right? Which happens to be 32,767 in decimal. So we need to know what that is so we can scale everything to that height. Now we can use a modulus division. There's an fmod function here which does a modulo operator and applies it to floating point numbers, which is exactly what we want for this, okay? So what this is going to do is, as we iterate through all the samples that need to be played to represent this total duration of time, we're going to take a counter and calculate that count value modulo the number of samples per period, which hopefully makes sense. So for ease of discussion here, all right, what is this thing doing? Let's assume that our sample rate is 1,000, and we want to play a note for 1 second, and let's assume the frequency is 10 hertz. So 1/10 of a second would be the total period, right, for 10 hertz. And in order to calculate how many samples you need for each one of those periods, it comes out to be 1/10 of the 1,000, which would then be 100, okay? So this all can work out nice and easy in our heads, okay? So if this then is 100, and I is going to go from 0 up to 1,000, what's going to happen is this modulus division is going to go from 0 to 99, then go from 0 to 99, then go from 0 to 99, and it'll do that 10 times over the 1,000 samples in this particular scenario, okay? So if we then take that value, which is going to be going from 0 to 99, and divide it by the 100 total samples per period, we're going to end up with a floating point value that starts out at 0 and actually goes up to, 0.99999, right? It'll be in the range of 0 to 1, okay? Which is exactly what we want for this line of code down here. So then what happens? Well, we know that if the angle right? We'll see this angle actually is the angle of a sine wave when we look at how sine waves are created. In a square wave, we know that because regardless of the frequency or anything else, this thing scales down to a simple value between 0 and 1. The first half of the period of the waveform, we want to express the value of the pressure to be at the maximum amount. So when the angle is less than a half, we want the waveform to be high and stay there until the angle becomes a half or greater, at which time we're going to send down the negative maximum. Okay, so this is where our square wave comes from. The first half of the waveform will be high. The second half will be low at the maximum value. We can then scale it to this amplitude if we want to. So if I say make the audio amplitude set to 1/2, and the square wave would then consume only half of the total possible vertical range. Now, once I have that sample in a variable, I can, remember, I got to save it in big endian format, okay? So again, I got to flip the bytes around if I'm on a Pentium. So I just simply change its value using the same function we did above and write it out in the same way we did above. So this is going to go through this loop and generate as many samples as necessary to represent this duration at the sample rate that the program is built for, which at this time it's 44,100 hertz. Okay, so how do we call this? Well, if we're in our main, we can just simply call square wave. We'll talk about some of the other fancy stuff in a minute. Remember that the first field is the duration. So for 1 second, I want to write out, let's say 1,000 hertz. And I want the volume to be set to, like 0.5, okay? Now, if we compile this and we run it, we save this into a file, and then we load that file into our tool. Look what happens here. Here's the first time we did it. It was just silent for a half a second. We can throw that one away. We don't care anymore. Here's the new file. We have a half a second of silence followed by 1 second of something. You notice the amplitude is only using up half of the maximum range here. Now with this particular tool, if I click there and I zoom in, there's a little magnifying glass here somewhere. There it is. We can have a look-see at what our waveform looks like. And there's our square wave. If we keep zooming in, by the way, this will eventually show you every single individual sample. So this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it has, 20-some that are high, followed by 20-some that are low, and then it repeats. And that kind of makes sense, right? If you have 44,100 hertz total, and you want to play a sound that is at 1 kilohertz, you ought to see a total of, 44.1 samples for each full wave, okay? So let's go ahead and back up a little bit and look at the wave on its own without all the little individual sample points, right? So what happens is we should then see what, the 22 or so samples that are high, followed by the 22 that are low, and so on, right? So let's go ahead and zoom all the way back out here and hit the home key and the space bar to play it. There's my 1 kilohertz square wave. Not bad for the hello world of sound programs, okay? Well, let's make it a little bit more interesting. If we're going to make sound, let's play some recognizable music, right? I mean, anybody can just make random noise or tones. Let's take a quick review of how music kind of works, right? We have this notion of octaves. An octave is defined as a sequence of 12 semitones. And each of these semitones represents 1/12th of a step from one octave to what we say is the next octave, right? On a piano, we all know that there are notes that have names like A, B, C, D, E, F, G, right? And of course, it depends on, the history of your country and so on and the type of music. But in Western style music, an octave has these 12 semitones, and each one of them is given a letter. Okay, an octave goes, for some reason, from C, D, E, F, G, A, B. Okay, now notice that's 8 notes out of the 12. Right now, if this was a piano, those letters represent the white keys, which are called the natural notes. Okay. Now, every now and then there's a black key on a piano, right? Notice this pattern in this diagram here. You got a natural note. You got one of these things. This is a sharp or a flat, depending on whether you're talking about one up from C or one down from D. Okay. So it's C, C sharp, D, D sharp. These are the black keys. Okay. Then you got 2 white keys, and then you have these 3 black keys, right? If we go back here and you look at a piano, what do you got? You've got this blue key right here, which we can see is the middle C on a piano. And that's a white key. This black one here is C sharp. There's D, D sharp, E, F, G, right? G flat, or, E sharp. Your G, G sharp. And this yellow one here is your A sharp, and your B. And after that, the whole thing repeats itself. So you got C, D, E, F, G, A, B, C, D, E, F, G, A, B, and so on. Now, if you look at this drawing of the piano, see how it says 1, 2, 3, 4, 5, 6, 7, and so on. If you tell somebody to play a C, now you can tell them to play middle C, and they would know that that's the one here in the middle of the keyboard. But if you just told the person to play a C, he'd say which one? Because there's a C in each one of these octaves. This is the first octave, second octave, third and fourth, and so on, right? So if you want to play the C down here, you tell the person to play C1. This one here is C2, and so on. So when we look at the notes, like we say over here, C5, well, that's the C that's right here. That's 1 C above middle C. We say that's 1 octave over middle C, all right? So with that in mind, when we come back and look at this thing, this kind of makes sense now, right? So there's the white keys, which have the natural notes, and you have your sharps and or the flats, depending on how you look at it. Now, why am I going on about this, right? Well, we need to figure out what frequencies we want to play, okay? That's why we're going on about this. So if we look in this table, it'll tell you what all the frequencies are. This is one of the most important ones right here. The frequency of the A in this octave right here, which is going to be A4. This is the 4th octave on the piano. This is called A440, or the concert A. Every note on the piano, and every note in the entire Western world of music, okay, from Beethoven to Mozart and so on, is all based on the notes that are derived out of this frequency right here. Now, we care about this because if we want to create an audio file and play it back, and you want to then play along with it with a piano or a guitar or something, or a harmonica, all those instruments are designed based on the same frequency table here, and you won't be able to play with it if these frequencies don't match. It'll sound wrong, okay? So let's generate a table and fill it up with all the proper frequencies for all these notes. Now, fortunately, the guys that define the MIDI system did us a bit of a favor here, right? Because they've numbered all their notes. All right? See, we get notes number 0 through 11, 12 through 23, and so on. And what you'll notice here is there's 12 notes per octave here. So A440 right here is a MIDI number in this range right here. So to find out which note number in here corresponds to A440, we go back up to this table up here and we look. If B4 was note number 71, the prior note to that is A sharp, and the one before that would be A4. So if you take the note number of B and you subtract 2 from it, you'd get the note number for A in that same octave if you're using this MIDI numbering scheme, which is what I'm going to use here. So here's B4, and that's going to be the 71, minus 2 is 69, and that is the MIDI note number for A440. All right, so how do you get the notes out of this table? Notice what happens in here. In order to increase by 1 octave, look what's happening here. The A in this octave right here is 440 hertz. The A in the 5th octave is 880. It's double, 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 okay? That's the definition of an octave right there. If the frequency doubles, it's 1 octave away. All the other notes between the 440 and the 880 represent, a 12th of a way step forward towards doubling. All right? That's all we got to deal with here, okay? So all we got to do is come up with a mathematical function that maps this range of numbers to the 12 steps around this frequency right here, okay? And so on for all the other octaves. So somebody already worked that out. It turns out it's surprisingly simple, and the answer is right here. Okay, it says for use with the MIDI, which stands for Musical Instrument Digital Interface, by the way. I should have mentioned that before. I'm sorry. Okay, the frequency mapping is defined by this formula right here. Okay, now if you want to convert a note number like number 69 to a frequency, you use this formula right here, where P is the note number. So if A440 is number 69, look at the math in here. 2 to the P, which would be 69 minus 69 is 0 over 12. That's 2 to the 0th power, which is 1 times 440. Looks good. At least it works for concert A, all right? Now, what if we look at the frequency of A5 instead of A4? Well, what would that one be? Well, that would be 69 plus 12 notes to go up to that next octave to get to A5, right? So if this is 69 plus 12 minus 69, the numerator of this fraction would then be 12. Over 12 is 1. So 2 to the 1 power is 2 times 440 equals 880. So a quick spot check of the sanity of this thing says it sounds like it could work. All right? I tell you, it does. The MIDI spec dictates that this is how you calculate the frequencies of each of the notes based on the MIDI note number. So all we need to do is write a loop and iterate through all the values of P. So there's 128 total notes. They go from note number 0 up to 127. So let's write a loop that fills in a table with all these frequencies so we can use them in our square wave function. So that's what's up here at the top of this file. I have a nice table full of floating point numbers for the 128 notes, all right? So I'm going to store the frequencies, and the index numbers in this array are going to be the MIDI note numbers. So how do we do that? We write a loop from 0 to 128. We calculate 2 to the I minus 69 over 12 times 440. We just type that in and just generate them all and stick them all in here, all right? This is going to probably be a relatively inefficient function. All right, so I'm going to do that once and only once when the program starts up, store them all in this table, and we can just look them up anytime we need them later on when we're playing them, all right? Now, I'm going to define some macros down here because I don't remember what all these numbers are over here. If we wanted to play a song and you Google around, find some sheet music online, you can look up and see, oh, you play a C and then an F, then an A, and so on. I'm going to go ahead and create these macros that have these numbers in here, and you can recognize the A440 right there, note number 69, is the value for A4, okay? Now, G sharp comes right before A4, and then you see G4, and so on. Now, look at what's happening with these alignment. It's just coincidental that the names of the sharps, I put a little S in there, right? So if you go from C to C sharp, and then D, D sharp, like this, you can actually see the piano in there. All these that are shifted right are the black keys, right? You got the 2 black keys, and then you got 3 black keys. Then you got 2 black keys, then you got 3 black keys, all right? So, again, we're mapping this thing right back to the piano, which is the most fundamental model of the 12 semitone octaves, okay? So now down here in the main, rather than just having, I'm going to play 1,000 hertz, right, for half a second, we don't have to do that. I can use that lookup table now, okay? Now remember, it's duration, frequency, and then amplitude down here, or volume. So what I'm going to do now is I'm going to play what? 4 notes. 1, 2, 3, 4 notes at these frequencies, C4, C5, C6, C5. So what I'm doing here is I'm going to play a note. I'm going to go up an octave, up a second octave, and then back down. Okay? Let's go ahead and put the if 0 down here. We don't have too much going on to clutter up the place. This will help you understand what an octave sounds like if you're not intimately familiar with it, all right? Now, we don't need to run Audacity and all that anymore. We know the thing works. We know what these things look like. I can pipe it right into A-Play on my Linux box, and it'll play the sound for me right here. All right, so what we had there is we had a note, we went up an octave, we went up another octave, and then back down an octave, all right? And each one of them played for a half a second. Now, if we do want to save it in a file and open it up in Audacity, we can actually look at the wavelengths if we want to. All right, so here's the old one, here's the new one. We've got more stuff going on in there. Let's just delete the old one here. Now, if we zoom in here, we can see a waveform. And, of course, it'll take me forever to scroll around in here. But I don't want to change the zoom. Watch what happens. All of a sudden, we increase an octave right here. So let's now zoom in right there. Okay, so we have a frequency whose period lasts this long here, right? Then we see all of a sudden it takes a shorter amount of time. It turns out this is oscillating, we say, at twice the rate as the one before. So this thing just leapt up 1 octave. Again, we played it at half the maximum amplitude, which is why the thing is a gap there on the top. Now if we zoom way back out, which I always had trouble with the scrolling on this thing. Here we go. And we go to the beginning of the file and play it in here. Well, back to our file. Let's look and see what else we can do. All right, so let's say, what are we going to do here? Okay, we can clown around and risk getting a violation from NBC, right? They have those chimes that they play. It turns out if you play G3, E4, C4, that would be the sound from the old NBC chimes that you used to hear at the beginning of programs. But I'm going to play G4 instead of G3, right? I have no idea if this is a violation of anything. But I think that they'll be okay with this. Just for one quick play here. All right. And of course, there's one dum dum dum, and this one just went dum dum dum. All right. So anyway, so you can play around with this if you know the notes of the sounds that you want to make. So let's make a leap forward here for fun. Let's play do, re, mi, fa, sol, la, ti, do. So I have this little function over here, and what it takes is a pointer to a function. All right, remember we just called square wave right here? We gave it a duration, we gave it a frequency, and we gave it a volume here. I'm going to write a function called do, re, mi. I'm going to tell it what function it needs to use to generate its waveforms, and I'm going to give it a volume, which is full volume at 1.0. Then I'm going to wait, play some silence, and again, this just writes a bunch of zeros into the file to waste time without making any sound. And then what we got is a sine wave, a sawtooth, and a triangle wave, a couple of different kinds of sounds. So this might help you understand what they meant by the timbre, right, of these waves. All right, so let's go ahead and compile this one. Let's go ahead and run it so we hear what it sounds like. All right, so as we saw it played, the note, the do, re, mi, fa, sol, la, ti, do, 4 times, using once a square wave, a sine wave, a sawtooth wave, and a triangle wave, all right? And I'll leave the code walkthrough as a task for the student. It's in here. You can download it and look at it if you want. The short of it is, from the square wave to the sine wave, the only difference is how we deal with the values over the cycle, right, over the period of one of the cycles of the waveform, okay? So you can clearly see I'm calling the sine function in here to convert a value that goes from 0 to 1. I have to convert it from that to a value that goes from 0 to 2 pi, because the sine here is in radians of this angle. And then I can, scale it based on the 16-bit value, and then multiply that by the scale for the volume setting, so it can be turned down if I want to. All right. The only difference between the square and the sine is this right here. Everything else is the same. And you'll see the same thing's true if you go on to what we call a sawtooth wave. All right. Look what's going on here. These two lines, only difference, okay? We just calculate the math a little bit differently. We're going to zoom in on these and see what they look like. A triangle wave, this one's a little bit more complicated. I couldn't off the top of my head just come up with a simple one-line piece of algebra that does it. Feel free to leave one in the comments below. I don't like it when I have to write code that does this, but what you'll see when we look at the waveform, there are 4 distinct portions of this, and in order to convert a value that goes from 0 to 1 into the different portions of the cycle as it goes from the 0 up and then back down and then back up again, I just used the first quarter, the second quarter, the third quarter, and the fourth quarter of these range of values to do that, okay? Now let's look at the do-re-mi code down here. Now, how does this thing work, right? Remember, we called do-re-mi. We passed it the address of the render function. So this here is how you declare a pointer to a function that takes 3 float arguments and returns a void, okay? That's the name of the variable right here. So notice here, I then call another function, and again, I pass that variable through to there, okay? And here's the amplitude that I passed into the do-re-mi function. So how does this thing work, right? Well, I'm going to call render a MIDI note. That's this function right above it right here, okay? So these kind of go together. I want to factor out all the noise out of here, right? So every time I do this, I'm going to have 2 lines of code, all right? Well, every time I play a note, I want to have a small bit of silence after that note. So if I play the same note twice in a row, I actually hear it deet, deet. I can hear them both. So it doesn't just sound like one note played twice as long. All right. So what have I done here? I've defined, we remember all this from grade school. If you're not into music at all, you got whole notes, half notes, and quarter notes, and all this other stuff. So what do I got? I have a whole note, which I'm going to use 1 whole second. All right. Which is 1 bar of music. Quarter note would obviously be that divided by 4. A half note is whatever that is divided by 2. Okay. Now, how long should I pause between playing of notes? I just picked a number. I just said wait a 32nd of a second between times when you play the notes. As you heard when it was cycling through the do-re-mi, there were little teeny silence periods between the various notes that were played. So let's look and see again how this works here, okay? So we got render MIDI note. We pass it how long we want it to play in seconds. We tell it how we want it to be rendered. We tell it what number of the MIDI note to play. Remember, these are the pound define macros up there. So what MIDI note number corresponds to C4. And we just pass the amplitude down. Those come in here, and what do? This is where we actually call the render function, right? So if I call this and I pass it my render square wave function, this is going to make me a square wave, all right? How long? Now, I want it to last for the full duration that was requested, minus that little pause time, minus that 32nd of a second, all right? And then I'm going to pass it the frequency from my notes table for whatever MIDI number was passed in the first case it was C4. Pass down that amplitude and it'll apply it appropriately as it goes. After that's done, I'm going to play a little bit of silence for a 32nd of a second. All right? How does silence work? Well, I'm going to just render a square wave for however long that is, the 32nd of a second. And I don't even care what frequency it is. Just set the amplitude to 0. So I'm going to just play a note with no amplitude whatsoever, and it will come out as silence, okay? So here's how the silence function works. This is what the render MIDI note thingy does, and in order to play the notes of an octave, I'm just going to go C, D, E, F, G, A, B, and then back to C, okay? And that's what you heard, all right? So down here we said play a square wave. Wait a little bit. Play a sine wave. Wait a little bit. Play a sawtooth. Wait a little bit. Play a triangle, okay? So this time, let's play the sound and save it into our test file. and look at it in Audacity again, right? And now you can actually see all these notes playing. We're going to see 9 notes here because I start and finish at the C for the next octave. So here's your C4, D4, E4, F, G, A, B, and then C again, right? We can throw away the old file, right? So we have, what do? We played a square wave, then we played the sine wave, sawtooth, and a triangle, right? So let's have a look-see in here and see what we're looking at here. So there's definitely a square wave there. We'll zoom back out. Whoa, too far. Now let's look at this one here. Now you see some weird warbling and whatnot. That's because this thing can't really render. It's because the resolution of the screen is too low to make it look right when you're zoomed that far out. So clearly this is a sine wave right here. Now what's next? This one over here. Let's zoom in on that one here. Okay, move it over to the little... This is what we call a sawtooth wave. Because if we look closely at a saw, this is what the teeth of a saw look like, right? Okay, so what's the next one? The next one was a triangle wave. We zoom in on that one. This is a triangle wave. It's sort of like a sawtooth, but it doesn't have that harsh, straight fall down in here before it goes up again. So this is, you know, like a pyramids, okay? If we go back and we play this one, you can actually hear, your brain can tell that this thing is square. It sounds harsh. These hard edges of the pressure going from low to high very quickly is very tough on your ears. The sine wave has a beautiful, smooth, flowing curve, and it sounds like like ooh, like you're singing an ooh, like the vowels, right? Square wave to me, and even the sawtooth with that hard edge, almost sounds like the sound, right? So if you scroll in again on this sawtooth, again, your brain is going to hear this really fast, hard slamming of the change in pressures there. The triangle, on the other hand, is going to sound somewhat more like the sine wave because it doesn't have anything super harsh. It's not as simple, round, and flowing as a sine wave, but it is not as harsh with that hard vertical line in there, right? Just for fun, I went ahead and put Mary Had a Little Lamb in here as well, right? I mean, if you have all the notes and they work correctly, why not? So if you turn this one on down here, you can play Mary Had a Little Lamb in a sine wave, triangle wave, or whatever, right? So what is Mary Had a Little Lamb but just more notes, okay? E, D, C, D, E, 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 D, 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 E, 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 and so on, right? So if we build this up, and we run that one, save it in our test file, go back up here, load our test file back in. Then we have our Mary Had a Little Lamb, right? So there's a Mary Had a Little Lamb, and you see this note is longer, right? Little lamb, and then little lamb, Mary, da, 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 and fleece was white as snow. So you see a whole note down here, right? And both Do Re Mi and Mary Had a Little Lamb are well over 150 years old. So I hope I don't have any copyright problems with those when I upload this thing to YouTube. Anyway, obviously you can play around with this. You can create any kind of frequencies you want. If you want to play chords and things like that, you simply play more than one frequency at the same time and add them together. You can do so by creating a whole separate program and creating many mono files and then combining them together with a tool like Audacity where you just keep loading them in like this, one after another. Now this is just 2 copies of the same file, so this wouldn't be particularly interesting to play the same thing over itself. All this would effectively do is end up making it louder, perhaps. So this wouldn't add any, sonic information to what's already there. But if you were to play the same thing twice, and you change the frequency of one of them, like move it up an octave, then the thing will sound like it's harmonizing with itself. And to do that, I will leave that as a task for the viewer. Thanks for watching. See you next time.